Hello students, this is a review of the unit review for Unit 4. I'm going to walk you through the stations that you saw in class, and hopefully you will be able to do them for the test that is coming up. The first question asks you to take B and C, which are 5, 1, and -3, -2, and transform them in 4 different ways. The first two are rotations, and you can see that the rotations rules are right here. The rotation of 90 degrees counterclockwise and the rotation of 180 degrees counterclockwise. They're right over here. For letters C and D, it's asking for 2 different reflections, and these 2 different rules are written here. My suggestion is that you use your flashcards that you made in class to just learn or memorize the rules, because we're not going to be providing them to you on the test. Alright, you'll notice that 5, 1 transformed to -1, 5. That transformation, that rotation, was because we're taking the last value, the y value, which in this case is 1, and we're bringing it to the front. And notice that the -y means that we're making that value its opposite sign. Now the first value, which is the x value, goes to the back. It goes to the new y value. And notice that it didn't change 5 to 5. Same thing happened with the rotation of 90 of C. -3 went to the back, stayed the same. -2 came to the front, changed. So that's that pattern that it is asking you to follow. That's the rule that it tells you. You can see the other rules that are here, and they're fairly straightforward. They're fairly similar to these other ones. In the practice problems, the first question asks you to do a transformation over the line x equals y. Well, you know x equals y is the same as y equals x. They're exactly equal. They're equivalent equations. So what we had to do was take 4, -1 and change the order of the 2 values, the coordinates. For number 2, it asks you to rotate around the origin, but it asks you to do it 90 degrees clockwise. Folks in class were a little confused about that, but clockwise is the opposite of counterclockwise, so that means whatever this measure is, we're going to subtract it from 360 and make that measurement counterclockwise. The rule for counterclockwise is written here, and the correct answer is below. For question number 3, it gives you a triangle, and it says the use of the axes is optional, so you don't even have to do any of this stuff. All you have to do is write it out in this way, and I highly suggest that you start writing out your transformations in this way. It tells you the transformation, in this case a rotation of 90 degrees. It gives you the original point. We call this the pre-image, and it transforms into the image, which is -2, 1. We switched the order, and the first value became negative. The second value kept its sign. The first value went to the back. The second value went to the front, changed its sign. Alright, for question number 4, it asks you to draw the reflection of ABCD over the line y equals 2. You had to draw y equals 2, which is this line. It's a horizontal line. And you also had to count the number of units away from that line for the original shape, the pre-image. So 1, 2, 3 for B. We went 3 down from y equals 2. It's a reflection, so it has to be exactly equivalent direction and exactly equivalent magnitude in the other direction. So we had to go 1, 2, 3 straight up. For C, it was 4 away from y equals 2, so we went up by 4. For D, it was 6 away, so we did the same thing up here. For A, it was 1, 2, 3, 4 away, so we did the same thing up here. That's the method that you're going to use to reflect over a line that is given to you. If they give you y is equal to 2, you do that. If they give you x is equal to a certain number, you're just going to count boxes horizontally. Y equals x is the same idea, except you're going to be going diagonally. Alright, that was the first page. And now we're moving on to the second page. This is translations and dilations. Again, it gives you a series of rules. One quick note, a translation of -1, 4, for example, means we're going to take -1 and combine it with the x value, 4 and combine it with the y value. You can also write it out as this vector, which is -1, 4. You can take a look at the correct answers there, and if you have any issues with them, well, I guess pause the video and try to work it out. For this first question, there was a typo on the page. It should have said D for dilation of 2. It would not make sense to do a translation of 2 because you need 2 numbers for a translation. You can see over here the translation requires 2 numbers. Anyway, a dilation means you take each of the values and multiply them. So 4 times 2 gives you 8. Negative 2 times 2 gives you negative 4. For question number 2 is a translation. 3 units down means we're taking the point and going downwards, which means we're going on the y-axis. So 3 units down is an indicator of what happens to the y. 1 unit to the right, that's an x value. So 1 unit to the right means we're adding 1 to the x value. You should be able to get that fairly easily. Another example of use of the axes being optional here for question number 3, we did the dilation by multiplying everything by 2, the scale factor of 2. We call scale factor this value here. We also called it the multiplier in class. For question 4, it does ask you to draw the translation. We circled the draw here because it was required for us to do that. The vector 2, negative 5 means we're sliding every point 2 horizontally in the positive direction and 5 vertically in the negative direction. We wrote out these coordinates because it asks us to state the coordinates. We must write the coordinates if it says state the coordinates. And that's all for page number 2, station number 2. Moving on to station number 3, this is compositions of transformations. This is when we take transformations and combine them together. If you take a look at the model problem, let's see if I can get it in frame here. The model problem asks you to do 2 different transformations. The first transformation in letter A is a translation of negative 1, 4, and then do the rotation of 90 degrees. Keep in mind that every time you look at a composition of transformations, that circle means we're combining these 2 transformations. It also means that this one goes first, and this one goes second. So we're stating the coordinates of B prime, B double prime, C double prime after these transformations, and you can see that we did the same procedure as before. We wrote out the pre-image, we did an arrow, we did the image, and then the only difference from before is that we're doing a second image because we're doing 2 different transformations. Take a look at these answers and make sure that you know the rules that are behind them. The rules are written on the pages beforehand, but just make sure you're familiar with them for the test. Again, you won't be getting them on the test. You have to remember them. So for practice problem number 1, ABC undergoes this sequence of transformations. It starts off with 4, 2, and it gives you vertex A double prime. So it says, well, here's where we start. Here's the correct answer. How do we do it? Oh, this one, let's see, let me skip to the other page here. Yeah, this one I was able to complete the problem here. I wrote out all the different transformations by taking 4, 2 and transforming them by the first translation, the first transformation and the second transformation. Each of them gave me a different answer, but only one of them matched negative 2, negative 4, and that was choice 2. Keep in mind, in a problem like this, you will have to sort of do a little bit of legwork to try to find the answer, but there's only one correct answer. So go and find it. Like, it's there, just keep figuring it out until you find it. For question number 2, it's an identification of transformations. There were no numbers here, there were just axes, but it was simple to see. We took this shape, which is ABC, and we slid it downwards and to the right, and then we reflected it. This should be a little r. We reflected it across the y-axis. Translation, then reflection. It was important for you to get it in that correct order. Another way you can tell that there's a reflection, here's a little trick for you. From A to B to C. The way I name this triangle is I go around in a counterclockwise manner. I'm going from A to B to C again. So if you see the mouse pointer is going counterclockwise. The second image here is going from A to B to C. Notice that the mouse pointer is going clockwise now. If that changes, it's called a change in orientation. When a change in orientation takes place, there must be a reflection somewhere. So I knew immediately that it was not choice 3 because translation and rotation, neither of those change orientation. Remember that. That's going to be a very important skill for you to remember. You can take a look at the correct answers here. These correct answers are very straightforward. All we had to do is do the 2 different transformations. I guess the real tricky part is making sure that you do the translation first here and then the reflection across the x-axis. We're following that order. Same thing with question number 4, except we're doing it in reverse. We have to describe a sequence of transformations that brings bike to golf. One quick note, B and G are the first letters of each quadrilateral, so B has to correspond to G. So if we slide this upwards, B is still on the left-hand side. Notice that G is on the right-hand side, so there's got to be a way to take this B, which is far away from that y-axis, and transform it into G, which is on the far side of the y-axis on the other side, it looks to me like it's definitely a reflection, because B has to flip over to G. So that's your trick. Again, you can use the orientation. BIKE, we're going around in a counterclockwise manner, but GOLF, we're going in a clockwise manner, so there must be some sort of reflection. All right, now station number 3. Let's go back to station number 4. Whoa, too big. All right, in station number 4, it asks you to name 3 different transformations that would map the figure onto itself. That's an example of line of symmetry or rotational symmetry. Notice that I drew 4 different lines, and I was almost accurate here. I drew 4 different lines that met in that center point, and you should know that these 4 lines are the only 4 lines you can draw for a square, because a square should have 4 lines of symmetry. A pentagon is going to have different lines of symmetry, 5 lines of symmetry. Triangle will have 3 lines of symmetry as long as they are regular shapes, that as long as all of the sides are the same length and all of the angles are the same measurement. Anyway, the lines of symmetry are named here. Y equals 2.5, that's a horizontal line at 2.5. X equals -1, that's a vertical line at -1. Here's a diagonal line, y equals x plus 3.5. It's this one, and it's so named because it hits the y-axis at 3.5, and it is increasing at a slope of 1. Same thing here. The slope is -1, and it hits the y-axis at 1.5. Those are 4 different examples of lines of symmetry, and then you have 3 different rotations. Keep in mind, I can rotate this shape 90 degrees, I can rotate it 180 degrees, I can rotate it 270 degrees, and it's still exactly the same shape. That's called rotational symmetry. What we do is we take 360 and divide it by the number of sides, that's n equals 4, and we get 90, which means I can rotate it 90 degrees. And then I can rotate it 90 degrees again, which is a total of 180. And I can rotate it 90 degrees again, which is a total of 270. We stop there, because if we rotate it another 90, that's 360. And any shape, doesn't matter what shape it is, if you rotate it 360 degrees, it's going to give you the same exact shape. Okay, let's move on to the practice problems. If we're looking at the first problem, it's asking for an appropriate degree, what is not an appropriate degree of rotation that would map a pentagon onto itself. 360 divided by 5 is going to give you 72. That's rotational symmetry formula. Now, 72 degrees is how much you can rotate the pentagon once. You can rotate the pentagon twice to get 72 times 2, which is 144. You can rotate it 3 times, which is 216. 4 times, which is 288. Why wouldn't we rotate it 5 times? I just said it. 5 times would be 72 times 5, which is 360. And we never say 360 as one of the rotational symmetry measurements. Anyway, all of these are in the answer choices except for 180. Imagine a pentagon that has the points on top. If you flip it, or if you rotate it 180 degrees, the point's going to be on the bottom. It's not exactly mapped onto itself. It doesn't cover itself up completely. For number 2, it gives you several lines of symmetry possible, and it says which one will not map the shape onto itself. A line of symmetry that is not in the center of the shape is not a line of symmetry. So this line, which is y equals 1, that is not going through the center of the shape. If it had said y equals -0.5, it would have worked, but this one does not. For question 3, which regular polygon has a minimum rotation of 45 degrees? We did an example like this in class. I know that 360 over n is going to give me the minimum degree of rotation for rotational symmetry. 360 over n is equal to 45. We don't know the n because we don't know which regular polygon it is. Many students had the tendency to solve for n equals 8, but did not state that it was an octagon. You must state, because it says which regular polygon, you must state it's an octagon. It could be a nonagon, it could be a decagon, it could be a triangle, but you have to name the shape. Last but not least, 2 lines of reflection. We just draw the lines and figure out the equations, and luckily most of the time these equations are going to have the same slope. It's either +1 or -1, and we just look for the y-intercept. In this case 10, in this case 0. You also could have rotated this shape 180 degrees, about 5,5, around 5,5. That's the center of rotation here. You could also have used, you could not have used 90, because then it would look different. That is the unit review for Unit 4. I hope you have good luck studying.